Okay, hello guys. Today I'm going to discuss one of the most tricky topics of subject CT3 that students struggle with, that is called as convolutions. Okay, so without any delay, I'll start talking about the topic. Okay, so the problem here is, what is the problem that we are addressing here? The problem is that there are two random variables. Okay, we have got two random variables, x and y. Okay, and if I consider the discrete case of this problem, that is x and y have some sort of discrete distribution. Okay, so I'm discussing the discrete case first. So what is known here? I know some things here. I know that x and y are independent. Okay, this is a fact that is known. Okay, and I know the individual probability density functions of x and y. So I know probability x and I know probability y. These functions are known to me. Okay, and what I want is I want the probability function of z. Okay, where z is equal to x plus y. So what I want is a probability function of the sum of x and y, right? That is what I want here. So there is a method of finding this. See, we have already discussed moment generating functions, and under you must have studied it before studying this topic. And under moment generating functions, there is an easy way of combining the MGFs of these two random variables x and y by multiplying their MGFs. And you can get the combined MGF of m x plus y t, and that would simply give you the distribution of z, which would enable you to get the probability function or probability density function of z, right? That is a simple method. But there are certain cases where you cannot use MGF, or your question might state that you have to use convolutions in the exam. Okay, so that is why this is another method that we are discussing. Okay, so given these things, I know the that x and y are independent. I know the probability functions of x and y. So I want to find the probability function of z given these things, such that z is equal to x plus y. So simply speaking, p z z. Okay, what is it equal to? It would be the sum of, okay, it would be the sum of all the cases of the combined probability function of x and y, such that such that x plus y is equal to z. That is what it would be. It would be the combined function of the probabilities of y, that is their combined function, and it would be added over all the possible values of x, all the values of x, such that x plus y is equal to z. Okay, so that is what it would be, right? This is common sense. Now, how do I find this function? The way of finding this function is, because I know that x and y are independent, I can write this as the sum of x, and I can actually call this the product of px into py, right? I can do that. I can do that because these are independent, and since independence applies, that the combined probability function is just a product of the marginal probability function, so I can do this. Now I know something here. In order to transform this, I know something here. I know that x plus y is equal to z. Okay, so I want to actually make this entire function only in terms of x, so that I can add up all the x's, and I want to get the result in terms of z. So I basically want to eliminate y here. Okay, so the way I will do that, the elimination of y is done using this equation. See, I know x plus y is equal to z. So basically y is equal to z minus x. Okay, so that is something I know. Now y is equal to z minus x, so I can actually write this function as the marginal probability function of x at x into the probability function of y at z minus x. Okay, so that is how you can transform this, because y is basically equal to z minus x. So now you will get the answer of this function, where all the x's, this function will add up for all the values of x such that x plus y is equal to z, and uh, and you will get in terms of it in terms of z, obviously. Okay, so what the students struggle with here is, so far it is very easy. What students struggle with is this range. Okay, defining the range of convolutions is often a problem for students. Okay, and that is what we are going to be concentrating the most on here, that how do I define the range of this x. Okay, because although this is over the entire range of x, uh, but y should also be considered, the range of y is also to be considered, because over a certain points where we'll get y will become undefined there for the entire range of x. I'll show you how that happens, and we'll learn how to define the range of this function through an example. Let's see an example. Okay, let's take an example. So first I am taking the discrete case only, and I'll discuss the continuous case of this definition soon enough. Okay. So let us consider this a discrete case where x follows a Poisson distribution with a parameter lambda, and y follows a Poisson distribution with a parameter of mu. Okay. So these are the two parameters that and under the Poisson distribution, the x can take the following values. X can take 0, 1, 2, 3, going up till infinite terms, and y can also take these values 0, 1, 2, 3, so on and so forth, right? So x and y both cannot be negative. That is something I know. Okay, so now let us just deal with this case, see how it works. Okay. um, let's start with the defining the convolution function. So p z is basically equal to the sum of um, all over the range of x, p x x into p y z minus x. Okay, so this is what I have. Now let us just put the values using the Poisson distribution function. So this becomes lambda to the power of x into e to the power of minus lambda over x factorial, right? And this one, it becomes mu to the power of z minus x now, and this one becomes e to the power of minus mu over z minus x, right? So this is what you have here. Now the next thing that I have to do here is some sort of adjustment has to take place, but before that I need to define the range of x. What would be the range of x? Okay, so basically we know that here x is greater than equal to 0. Okay, and y is also greater than equal to 0. Okay, so let us try and define the range of x using these things. Okay, so if I try to define the range of x using these facts, the first fact that I know is this one. This is the first thing that I know, that x should be greater than equal to 0. The second thing that I need know from this is that y is equal to z minus x, which is greater than 0, right? So this would imply that z is less than equal to x. This is another fact that you will get out of this thing. Okay, so the second definition tells me that z is less than equal to x. Okay, so these are the two things that I will get to know from these two definitions. So basically the range of x will be based on these two things. It would be greater than x, it would be greater than 0, okay, but it would be less than z. So x would go from 0 to z, okay, greater than equal to 0 and less than equal to z. So it will go from 0 to z, and I'll have lambda to the power of x e to the power of minus lambda over x factorial into mu to the power of z minus x into e to the power of minus mu over z minus x factorial. Okay, so this is what I have here. Okay, now let's move on. Now let's try to simplify this function. So I am going to take all the constant terms out which do not contain x. So this e to the power of minus lambda plus mu, this thing would come out, and all the other terms they contain x. Um, yeah, they do. Okay. So inside I would be left with x goes from 0 to z, lambda to the power of x, e to the power, okay, this is gone, this term is gone. I'll have an x factorial. I have mu to the power of z minus x over z minus x factorial. Now there is a little adjustment that is required here. What I would do is I would multiply and divide this entire thing by by z factorial. Okay, I'm multiplying and dividing this thing by z factorial, and you'll get to know in the next step why did I do this. So I just have e to the power of minus lambda plus mu over z factorial, and inside I have a x going from 0 to z. Okay, and here I have a z factorial over x factorial into z minus x factorial. Okay, and inside I have a lambda to the power of x and mu to the power of z minus x. Now I'm going to tell you the reason for why I did what I did. Okay, so this entire thing, this z factorial over x factorial and into z minus x factorial, this is nothing but zcx. Okay, this is the combination function. Okay, so that's why I did this. In order to get this combination function, I multiplied and divided by z factorial, lambda to the power of x, mu to the power of z minus x, e to the power of minus mu plus lambda over z factorial. Okay, now there is another little adjustment here. See, I know that x plus let's say x plus y whole to the power of n is basically equal to going from let's refine a dummy random variable j going from 0 to n, um, n c j x to the power of n, sorry, x to the power of j and y to the power of n minus j. Okay, this is your expansion, this is your expansion for x plus y to the power of n, and you know this. Okay, this is a very standard formula. I'm forgetting what they call this. Okay, I'm not able to remember this, but this is your formula for x plus y to the power of n, and using this formula you can actually find any power of x plus y. So that is going from j is equal to 0 to n, n c j x to the power of j and y to the power of n minus j. That is how you expand it. Okay, so if you try to draw a parallelism between this formula and this formula, you will realize that this is nothing but see, same ncj zcx, uh, lambda to the power of x, x to the power of j, mu to the power of n minus j, z minus x. So it is exactly the same thing, and this can be written as, this thing can be written as lambda plus mu whole to the power of, see, I've got n here, z here, so z. Okay, and in place of x and y I had lambda and mu. Okay, so this is what you can write this as, and this becomes e to the power of minus lambda plus mu over z factorial. Okay, so this is what you have. This is called as a binomial expansion. Yeah, now I remember it is called as a binomial expansion. So since we have this binomial expansion, I can write it like this. Okay, now this is your answer for this, and you can clearly see that this is the uh, probability function of z following a Poisson distribution with parameters mu plus lambda. Okay, so that is what z follows, and this is your probability function for z, which I found by multiplying the marginal probability functions of x and y and adding them up over all the values of x. Okay, so this is your discrete case for this thing. Now we'll move on to the continuous case, but I want you to remember the same principles using which we had defined these things. We had defined the range of x in terms of z. Okay, so that is how we do it. Okay, so I want you to remember this thing, these two things. We'll be applying the same principles again. Okay, so next thing I do is I move to the continuous case of convolutions, and here, see, obviously, as we had the probability mass functions in the last part, I'm sorry, by mistake I might have called them probability density functions, but they were probability mass functions because we were talking about your discrete case. But now we would be dealing with probability density functions. Okay, so that is basically your continuous case, that is x follows a continuous distribution and y also follows a continuous distribution, and I want to find the distribution of z, which is x, which is x plus y, right? That is what I need. Okay, so let us just start with this. The probability the probability density function of z is basically equal to the integral over the entire range of x. Now, similarly, in place of the probability mass functions, this time we will have the probability density function. So it is basically the combined probability density function of x and y. Okay, x and y, such that okay, let's call them x and y for starters, and then I'll just apply this thing. Okay, so this is it. Okay, now since x and y are independent, they just multiply. So the combined probability density function is just a product of the marginal density functions. So it just becomes pf capital X small x into f capital Y small y. Okay, and dx, right? So now what happens is I write the y function in terms of z and x. So y is basically equal to z minus x. Okay, so over the entire range of x, f capital X small x, f capital Y, uh, and inside small z minus x dx, right? So this is your definition for the convolutions and the way to find the um, density function of z, which is equal to x plus y. Okay, and again the way of defining the range of x would be the same. So let us discuss a case where x follows a exponential lambda distribution and y follows a exponential mu distribution, very similar to the last case. Okay, this is almost parallel to that. Okay, so your density function for z would be equal to the integral over the entire range of x. Now fxx becomes lambda e to the power of minus lambda x, and this one becomes mu e to the power of minus mu z minus x. Okay, so that's what you have here, and this becomes dx. Okay, defining the range of this again. Now x is we have got two equations. We have got x is greater than 0 and we have got y is greater than 0. So this is your first equation, and the second one is that y is greater than 0. This implies that z minus x is greater than 0. This implies that z is greater than x. So basically x goes from 0 to z, that is x is greater than 0 but it is less than z. Okay, so obviously I always want the range to be in the terms of z because I want the final answer to be in terms of z. So the range can always contain either a constant, okay, or it can contain z, and it cannot contain any other random variable. Okay, it cannot contain x or y. The range cannot contain x or y, right? So that is something I wanted to know. Okay, so now this how do we solve this? Let's take the constants out. Okay, lambda into mu comes out. Okay, and e to the power of minus mu z also comes out, because for the reason that it is a constant. So inside I just have e to the power of minus lambda plus mu, okay, into x dx. Now let us just integrate this to get the answer. So this becomes lambda into mu into e to the power of minus lambda z. Was it lambda or was it mu? Okay, this was e to the power of minus mu z. Let us correct that, because z was only with mu and not with lambda. So let us just correct that. Okay, so this is e to the power of minus mu z. Okay, that is what came out of this thing. Okay, so and also this is here x is positive, so this would be a negative sign here. Okay, because mu x, if I multiply minus mu with minus x, that becomes plus mu x, and since I have in the power already a negative sign, so I've taken inside a negative sign in order to make it plus mu x. Okay, that's what I'm doing. Okay, so this would be my result here. Now I'll have lambda into mu and e to the power of minus mu z. Okay, and inside if I integrate this becomes e to the power of minus lambda minus mu over x divided by minus lambda minus mu. Okay, and going from 0 to z. Okay, so when I put let's do this. Let's take the minus sign out of these two, into mu into e to the power of minus mu z. Okay, so inside when I've taken this minus sign out, okay, it's here, and inside when I put the value z and 0, let's see what happens. So this lambda minus mu also comes out because it's a constant. Okay. So when I put z, it becomes e to the power of minus lambda minus mu z, and when I put 0, it just becomes 1. Okay, so the next thing I do is I multiply this e to the power of minus mu z inside, and also this minus sign inside. Okay, so I'm taking the minus sign inside and e to the power of minus mu z inside. So lambda upon mu, lambda minus mu stays the same. Okay, inside if I multiply the minus sign inside, this term it becomes negative and it is multiplied with e to the power of minus mu z. So here we have got a e to the power of minus mu z, so that is e to the power of plus mu z, and this is e to the power of minus mu z outside. So they multiply to cancel out, and this becomes e to the power minus lambda z because mu is gone, and I have a, and this is obviously negative because I'm multiplying the minus sign inside, and if I multiply this part with this one, this becomes a plus e to the power of minus mu z. Okay, so this is your final answer for this function, that is lambda mu lambda minus mu, and inside I have a e to the power of minus mu z minus e to the power of minus lambda z. Okay, so that's your probability function for z. Okay guys, so that was the basic idea of convolution in the discrete and continuous cases. Actually, I'm going to make one more video on a bit complicated examples of convolutions, because uh, a few times there have been a few complicated exam questions on convolutions, and I want to make a video on them, but that would come a few days later. Till then, I want you to be patient, and if you have some good questions on convolution in which you have a doubt and you are not able to solve them, you can just message me, you can WhatsApp me. Okay, you can WhatsApp me at this number, and you can send your questions here, and I would make it sure that I include those questions in my next video on convolutions. Okay, so this was your basically your basics of convolution. The complicated examples would be covered in the next video.